Okay, so last time we began chapter 4, we were discussing divisibility and modular arithmetic. Okay, so we discussed what divisibility means, right? We said A divides B means that A is a factor of B, or in other words, that if A is an integer, I can multiply it by some other integer, call it C, to get B. All right, and we write it this way. That means A divides B. Okay. We discussed a couple of theorems. We also discussed among them the division algorithm, which basically stated that if you take one integer and divide by a positive integer, you have a unique quotient and remainder, right? So if A is divided by D, then there's a unique Q and R, unique quotient and remainder, such that A equals D times Q plus R. Okay. We said that A div D is a shortcut, or is a expression that means the quotient, and that A mod D is an expression that means the remainder R. Okay. All right. We discussed congruence modulo M as well. So we just talked about A being congruent to B mod M. And that's congruence modulo M. All right. And we said two integers A and B are congruent mod M or modulo M if their difference is divisible by M, right? M divides their difference. Or in other words, that's the same thing as saying that A and B have the same remainder when divided by M. Okay, and we discussed a couple of theorems about that. And then we also discussed arithmetic modulo M. Right, if you have some set Z sub M, right, how to add and multiply elements on that set. Okay, so that about covers everything we discussed last time. Does anybody have any questions or homework questions? Question 3. All right, let me take a look. Give me one moment. Question 3 asks you to prove that part 2 of theorem 1 is true. Okay. So that's referring to part 2 of the first theorem we discussed last time, that theorem that had 3 parts. Okay, so if you want, we can go over that. All right, so part 2 of the theorem, let me rewrite it, was as follows. A, B, and C are integers. A is not equal to 0. Then, if A divides B, then A divides B times C for all integers C. Okay, so this is a conditional statement. Just do a direct proof, right? Assume A divides B. So if A divides B, then that means that B equals to A times some integer, let's call it S. All right. So we need to show that A will divide B times C. Okay, so what is B times C? I'm not sort of writing everything out. I'm doing a little bit of a shorthand here, but what is B times C going to be? Well, B is A times S. So that's A times S times C. That's A times S times C. I'm just rearranging the parentheses. So A is a factor here, so that means A divides it. Okay. So A divides A times S times C, since it's a factor. And that means that A divides B times C, and you're done. Okay, right, A is a factor. Okay. Next question was, is this similar to computer science algorithms? I'm not sure what you're referring to with that. I apologize. Okay. The question after it was for 9 B, G, and H. Let me take a look in one moment. Okay. Okay, so for number 9, you're asked, what are the quotient and remainder? And for B, you're given negative 111 and 11. Okay. So what is the quotient and what's the remainder? That's what you're, so to speak, what you're being asked here. All right. All right, well, how many times does 11 go into negative 111? Okay. All right. 10 times, right? The only problem is if we make our quotient 10, okay, well, actually it would have to be negative 10, right? If it goes in negative 10 times, all right, then your remainder will have to be negative. And remember, we said we always want our remainder to be a positive number. Okay, right? So in order to make the remainder a positive number, I have to make this negative 11. And that would be negative 121. And then my remainder will be plus 10. So that Q is negative 11. The remainder is 10. Okay, so you choose your quotient so that your remainder will be positive. All right. And then G and H are probably similar to that. Let's see. Number 9. Oh no, actually 9G is a little bit different here. Let's see. So you're asked what are the quotient and remainder when negative 1 is divided by 3? Okay. All right. So for this one, all right, 3 goes into negative 1. Well, if you say 0 times, then your remainder will have to be negative 1. All right. And again, the remainder will come out negative. So I'm going to go down by 1. I'm going to make it negative 1. Okay, which is the same thing I did in the previous problem. Instead of negative 10, I went down by 1 to negative 11. So here, instead of making it 0, I'll make it negative 1. I go down by 1. 3 times negative 1 will be negative 3. So then that just makes my remainder 2. Okay. So you always, with the negative numbers, you go down by 1. So this way your remainder will be a positive number. Okay, you pick your quotient so that the remainder will be positive. All right. And then for H, you're asked, what about when 4 is divided by 1? Okay. So when 4 is divided by 1, 1 goes into 4 times, plus a remainder of 0. Okay, so Q is 4. The remainder is 0. Okay, so I said that the remainder has to be positive. I sort of misspoke. It has to be non-negative. All right, so greater than or equal to 0, but less than the divisor. Okay. All right, next question was 13E. Give me one moment here to look that up. Suppose that A and B are integers. A is congruent to 4 mod 13. B is congruent to 9 mod 13. Find the integer C with C between 0 and 12 such that, and for E, you're told C is congruent to A squared plus B squared mod 13. Okay. All right, so A is congruent to 4 mod 13. B is congruent to 9 mod 13. Find some number C, some integer C, with C between 0 and 12, such that C is congruent to A squared plus B squared mod 13. Okay, so one of our theorems was that if I have congruences, I can multiply them and add them as long as the modulus is the same. And the congruence will still be true. Okay, So what I'm going to do is I'm going to figure out what a squared plus b squared is supposed to be congruent to. Okay. If a is congruent to 4, then that means I'm going to plug in 4 for a and 9 for b. Okay, so c has to be congruent to 4 squared plus 9 squared mod 13. Okay, and again, I'm allowed to do this because of the theorem that we said that I can multiply and add congruences with the same modulus, and the congruence will hold. Okay, the congruence will still be true. All right, so 4 squared is going to be 16. 9 squared is 81 mod 13. 16 plus 81 is going to be 97. Okay, so I need to find some number c, some integer c, that's congruent to a squared plus b squared. A squared plus b squared is 97. So I have to find a c congruent to 97 mod 13. And c has to be a number between 0 and 12, inclusive. Okay? So what should c be? Right. So what I would do for this type of problem is I would just find what's the remainder when 97 is divided by 13. Okay, because that remainder will have to be a number between 0 and 12. And just make c that number. Okay, that number will be congruent to 97 mod 13. And it will also be between 0 and 12. Okay, so let's find what 97 is divided by 13. How many times does 13 go into 97? 7 times? Fine. What's the remainder? 6. Okay, I'll take your word for it. So the remainder is 6. Okay, so 6, if I divide, by the way, if I divide 6 by 13, right? How many times does 13 go into 6? 0 times plus a remainder of 6. Okay, so 97 and 6 have the same remainder when divided by 13. So they're congruent to each other. So 6 is congruent to 97 mod 13. Okay, so let's c equal to 6. All right, that's a number between 0 and 12. That's congruent to 97 mod 13. So it fits the bill. That's what we're looking for. Okay. Oh, it was given to you in the problem. So how do you know a is congruent to 4 and b is congruent to 9? That you were told that at the beginning. Let a is an integer congruent to 4, b is congruent to 9. Find c. Okay, so that was given to you. Okay. All right. Any other questions? Okay, so if there's no other questions, then let's continue. Okay, so we're now going to move on to section 4.2. Okay, which deals with integer representations. Okay. All right, so in this section, we're going to discuss writing integers in different bases, right? Specifically base 2, which is also called binary, base 8, which is called octal, and base 16, which is also called hexadecimal, right? Our number system that we usually use is base 10, which is called decimal, all right? Okay, so we're going to discuss writing integers in other bases. Okay. All right. So first of all, as I said just a second ago, our number system is decimal, right? Which is base 10. Why is it called base 10 or decimal? Deci for 10. Because there are 10 digits that are used to represent numbers in base 10. Okay. Those are the digits 0 through 10, 0, 1, excuse me, 0 through 9. Okay, right. So those are, in other words, z sub 9. Okay. Z sub 10. Excuse me. Okay. All right. So every number in base 10 is written using these 10 digits. Okay. So if I look at a number, let's say I look at the number 3,402. Okay. 3,402. When I write that down, what does that mean? So in base 10, this means 3 times 1,000 plus 4 times 100 plus 0 times 10 plus 2 times 1. In other words, it means I've got 2 ones, 0 tens, 400s, and 3,000s, right? Or if I can also think of this as being powers of 10. So this is the same thing as 3 times 10 cubed plus 4 times 10 squared plus 0 times 10 to the power of 1 plus 2 times 10 to the power of 0, which is just 1. Okay. All right. So in decimal, in base 10, everything is really just powers of 10. And how many powers of 10s do you have? And you add them up, right? The ones place, the tens place, the hundreds, the thousands, the 10,000s place. Those are all really just powers of 10. Okay. All right. So when we write numbers in other bases, we're basically just using a number other than 10 as our base. Okay, that's why it's called base 10, because 10 is the base and the powers change. Okay. All right. So let me give you a theorem here, and then we'll discuss different bases. So let b be an integer greater than 1. Then, if n is a positive integer, it can be expressed uniquely in the form n equals a sub k times b to the power of k plus a sub k minus 1 times b to the power k minus 1 plus, and then following this pattern, dot, 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 plus a1 times b to the power of 1 plus a0 times b to the power of 0, which b to the power of 0 is really just 1, so I'll erase it. All right, we don't even need to write it there. Okay. So take any integer n, any positive integer n, okay. I can write it in any base I want in this form, okay, where k is a non-negative integer, a0, a1, all the way up to a sub k are non-negative integers less than b. And a sub k is not equal to 0. Okay. All right, this is called the base b expansion of n. Okay, so this is okay. All right, so again, I repeat, this just basically tells us that you can write any number from decimal into any other base you want, with this sort of formula here being our conversion. Okay, So we'll start with binary, or with base 2. All right. So let me scroll up here a little bit. Binary, which is base 2. Okay, so let's say I want to write numbers. I want to express numbers using only two digits, a 0 and a 1. Okay, base 2, I've got only 2 digits. So I'm only using zeros and ones. Okay, in binary, we use zeros and ones to represent all our numbers. All right. So every number is going to be expressed using only zeros and ones, except now, instead of every place being a power of 10, it's going to be a power of 2. Okay, so everything is multiplied by powers of 2. Every 0 and every 1 represents power of 2. Okay, so let me give you an example, and let me demonstrate how we understand this by way of example. All right. So let me actually write this first. In base 2, every integer is represented using only zeros and ones. Okay. So let's say I ask you, what is the decimal expansion of 1011? Okay. So I've given you here 1011. It's written in parentheses with a subscript of 2. Okay, so that subscript of 2 tells me that this number is a binary number. It's base 2. Okay, we do that sometimes just to let you know what the base is. All right. So I've given you a number in binary, 1011. And the question is asking you, what is the decimal expansion of this number? In other words, what is this number in decimal, in base 10? In our number system, what is this number? Okay. So how do I figure that out? So remember what I just said a moment ago. Everything in binary is based on powers of 2. So 1011, what is that equal to? Okay. That's equal to, so what I'm going to do here is I'm going to write I'm going to take each digit, the 1, the 0, the 1, and the 1. I'm going to space them out. Oh, that should be a 0. And I'm going to leave my parentheses next to them empty for a moment. So I wrote 1, 0, 1, 1. I spaced them out with pluses in the middle. Okay, I left parentheses, okay? Let me go all the way over to the right first, okay? The first one all the way to the right, okay, this one here that I just circled, that one, which now I'm underlining over here, this one all the way to the right is multiplied by 2 to the power of 0, okay? Everything is going to be multiplied by powers of 2. Starting all the way out the right, I start with 2 to the power of 0. As I move to the left, each time the power of 2 is going to increase by 1. Okay, so it starts with 1 times 2 to the 0. Next is times 2 to the power of 1. Over to the left, it's times 2 squared, and then 2 cubed. Okay. All right, so each time I move over to the left, the power of 2 goes up by 1. All right, so to figure out what this is in decimal, I just have to multiply and add this all up, and that will give me the decimal expansion. So this is 2 to the third, which is 8, plus 0 times 2 squared, well, 2 squared is 4, but times plus 0, plus 2 plus 1, which is, as somebody said, somebody wrote in the chat here, that's 11. So what is the decimal expansion of 1011? It's 11, okay, in base 10. And to let you know it's base 10, I'll just put a little 10 there. Okay. All right, so in other words, if I look at the number 1011, okay, that's in binary, it's telling me I've got 1. This tells me I have 1, 2 to the power of 0, or in other words, 2 to the power of 0 is 1. So I've got 1, 1. I've got 1, 2. I've got 0 4s and 1 8. Okay. And then you just add up the ones that you have. So it's 8 plus 2 plus 1, which gives me 11. All right. Any questions on that? All right, let me give you another example here. What is the decimal expansion of 1, 0, 1, 0, 1, 1, 1, 1, 1? So what is this number in decimal? Okay. All right, so what I'm going to do is I'm going to write them all out, okay, and space them out, multiply them by their appropriate powers of 2, and add them all up. Okay, so it's going to be 1 times 2 to some power plus 0 times 2 to some power plus 1 times 2 to a power. So it's 1, 0, 1, 0, 1. I messed up this. Sorry, let me fix that. 1, 0, 1, 0, 1. And then followed by 4 ones. So 1. Right, 1, 0, 1, 0, 1, 1, 1, 1, 1. Oh, I got an extra one there. Okay. Okay. So that's going to be, starting all the way out on the right, that's 2 to the power of 0 times 2 to the power of 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, to the 7th, to the 8th. Okay. Multiply and add that all up, you'll get that this thing is equal to 351. So that is its decimal expansion. I'll just leave it like that. Okay, so that would be the answer. So this is the number 351 written as binary. Okay. Okay, questions on that? All right. Let's discuss some other bases. So let's now discuss base 8, octal. Okay. If you want to write numbers in base 8, you're only allowed to use 8 digits. Those are the digits 0 through 7. Okay. So in octal, we use only these 8 digits to represent every number, every integer. What does 351 mean? 351 is what the number is, okay, in base 10. So the number 10101, 1111, what number is that? That represents a number, an integer. That's the number 351 in our number system. Okay, that's base 10. If you want, you can even, if you want, I could write it with like that, okay? Okay, what is base 10? That's what I was discussing at the beginning. All right. Base 10, in other words, the way we write numbers, okay, we write numbers using 10 digits. Okay, so that's called base 10. Okay, because everything is based on powers of 10. All right, if we go back to, if you scroll back to the beginning here, let me scroll back. I'll scroll back for just a moment. Okay. If I write down the number 3,402, Okay, this is a number. It's a number written in base 10. Why? Because it's based on powers of 10, where 10 is the base, right? What does it mean? It means I've got 3 thousands, or 3 10 to the power of 3s, plus 4 hundreds, or 4 10 squareds, plus 0 tens, plus 2 ones, which are 10 to the power of 0. Okay. All right. So anytime you write down a number, it's in base 10. All right. Does that sort of answer your question? Okay, great. All right, so what we're doing now is we're basically saying that if we want, we can represent numbers with less digits. We can say every number will be represented using only 2 digits, 0 and 1. Okay, so how do I do that? Well, here's how you do it. We're now going to discuss base 8, writing out numbers using only the numbers 0 through 7. So if you're only allowed to use the digits 0 through 7, you're in base 8. How would you write out numbers? Okay. So in base 8, you're only allowed to use the digits 0 through 7 to represent every number, okay? So if I wanted to write down the number 5 in base 8, that would be just 5. Right? 5 in base 8 would be 5. 6 in base 8 is the number 6. 7 in base 8 is the number 7. What if I wanted to write the number 8 in base 8? Okay. How would I have to do it? How would I write 8 in base 8? I would write it as 1, 0. Okay. 7, I have no digit 8. Oh, well, excuse me. I did that backwards. Okay. 8 in base 8 would have to be written as 1, 0. Okay. The 1 represents an 8, and the 0 means I've got 0 in the 1's place. Okay. So that's 8 plus 0, which is 8. All right. Let me give you a better example. Okay. Let's ask you, what is the decimal expansion of 7016? Okay, so here is a number in base 8. I'm asking you to write it in decimal. Okay. I'm gonna do a better example here. Let's do this one here. What is the decimal expansion of 7016? Okay, so here's a number in base 8. I want you to convert it to base 10. Okay. All right, so we're going to do the same thing we did before. I'm going to write 7016. Okay. And I'm going to multiply them by powers of 8. So starting all the way on the right with the 6, I'm going to multiply it by 8 to the power of 0. Okay. Why am I multiplying by 8? Because 8 is my base now. So everything is based on powers of 8. Right. The next thing, the 1, is multiplied by 8 to the power of 1. The 0, 8 squared. And then the next one is 8 cubed. Okay. So what is this number as a decimal number? I multiplied by the powers of 8. I add them up, and you'll get that this is 3,598. Okay. Okay, so again, I'm multiplying by powers of 8 to get the decimal expansion. Why? Because this is in base 8. Okay, so I'm telling you now how to go from other bases to decimal. We did before from binary to decimal. Now we're doing from octal to decimal. Okay. All right, there is one more base I want to discuss, which is hexadecimal. That's base 16. Okay, so if you want to write numbers in hexadecimal in base 16, you use 16 digits. Okay, the numbers 0 through 9. Okay, and then 10 through 15. However, for 10, 11, 12, 13, 14, and 15, we have letters to represent those numbers. So A will represent 10, B 11, C is 12, D is 13, E is 14, and F is 15. Okay, so A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay. Why is it lettered not numbered? So that we have, well, so that we have a single, I could really give you two reasons. I'll give you one. So we have a single symbol to represent each digit. Okay. All right. All right. So let's say I ask you, okay, let's say I ask you, what is the decimal expansion of 2AE 0B? Okay, so here is a number written in base 16, 2AE 0B. That's a number, okay? It's some integer. And I've written it out in base 16. Okay, so we want to convert it. It's almost like we're translating, right, from one language to another. We want to convert it from base 16 to decimal. Okay, so how do we do that? The same thing we did before, except now we're multiplying by powers of 16. Okay, so I'm going to space out all of my digits here. Okay, 2AE0B. All right. The second answer to your question, by the way, is if instead of A, I wrote 10 here, I wouldn't know that it's 10. I would think it's 1 and 0 separately. I wouldn't know that they're together. Okay. All right, so 2AE0B. I'm going to multiply everything by powers of 16. Why? Because this is base 16. It's hexadecimal. All right, so B, I multiply by 16 to the power of 0. I always start with powers of 0. Then 0 here I multiply by 16 to the power of 1. Okay. Then 16 squared. Then 16 cubed. And then 16 to the power of 4. Okay. Now, in order to do this, at this point, we're going to convert the A, the E, and the B. We're going to convert the letters into their decimal numbers. So I'm going to write this as 2 times 16 to the 4th plus A is 10 times 16 cubed. E, we said, is 14. So plus 14 times 16 squared plus 0 times 16 to the power of 1 plus B is 11. 16 to the 0 is just 1. Okay, so you take out your calculator, you plug that in, and you get that this is 175,627. Okay, so the number 2AE0B in hexadecimal, what is that number? That is the number 175,627.
Professor, I didn't
Yes.
get the part where you assumed A, E, and B equals to 10, 14, and 11.
All right, well, A represents 10. So at this point, I just write it as 10 here. Okay, A is 10, B is 11, and so on and so forth.
Oh, okay. There is already number given.
Okay. All right. So when you're doing hexadecimal, you got to remember A, B, C, D, E, and F, what they represent, right? A is 10, B 11, and so on and so forth. Okay. So that's what we're going to discuss now. All right, so the next thing, so far we've discussed going from other bases to base 10. We're now going to discuss writing numbers from base 10 into other bases. Okay, converting from base 10 to a different base. All right. Okay, so remember, if you're given something in some base other than 10, and you want to write it in base 10, you multiply by powers of the base. So if you're in base 16 and you want to go to base 10, you multiply by powers of 16. If you're in base 8 and you want to go to base 10, you multiply by powers of 8. And if you want to go from binary base 2 to base 10, you multiply by powers of 2. Okay, let's discuss the reverse now. All right. Okay. So to go from base 10 to other bases, okay, there's a little bit of an algorithm. Okay, so I'm going to demonstrate the algorithm with an example. Let me briefly describe it now. So to go from base 10 to other bases, divide the number by the desired base. And write Q and R, the quotient and remainder, in the form from the division algorithm. Okay. Okay. Next, divide Q, your quotient, whatever your quotient was, by the desired base. Again, writing it out using the division algorithm. Okay. Keep doing this until Q is 0. Okay. The answer will be the remainders written in reverse order. And I'll explain what that means in a moment. Okay. All right, so let me demonstrate this algorithm here with an example. Let's say I ask you find the binary expansion of 241. Okay, so 241 is a number written in base 10. I'm asking you to find its binary expansion. In other words, write it as a binary number. Okay. So how would we write 241 using only zeros and ones? So what we're going to do is I'm going to take 241, and using the form from the division algorithm, I'm going to find the quotient and remainder. So what am I going to divide by? I'm dividing 241 by the base that I want to change to. So since I want to change to binary, that's base 2, I'm going to divide by 2. Okay, so my divisor is 2. 241 divided by 2. How many times does 2 go into 241? 120. Right? 2 times 120 is 240, plus a remainder of 1. Okay, so my quotient here is 120. That's the Q. My remainder is 1. Okay. The next step is going to be to take the quotient that we got, 120, and now divide that by 2. Okay, so 2 goes into 120 60 times, plus a remainder of 0, right? 2 times 60 is 120. Okay, now I'm going to continue doing this. I'm going to keep doing this until my quotient is 0. So I'm going to take the new quotient that I got, 60, divide that by 2. 2 goes into 60 30 times, plus a remainder of 0. Okay, take the quotient again, 30, Divide that by 2. 2 goes into 30 15 times, plus a remainder of 0. Okay. Take the new quotient 15, divide that by 2. 2 goes into 15 7 times, plus a remainder of 1. Keep going. 7 equals to 2 times. 2 goes into 7 3 times. 2 times 3 is 6, plus a remainder of 1. All right. My new quotient is 3. 2 goes into 3 once, plus a remainder of 1. Right? 2 times 1 plus 1 is 3. My quotient is now 1. 2 goes into 1 0 times. Right? 1 divided by 2 is 0, plus a remainder of 1. Okay. My quotient is now 0, so at this point we stop. Right? Stop when q is 0. All right, so what is the binary expansion of 241? My answer is the remainders in reverse order. So meaning written from bottom to top here. So it's going to be 1, 1, 1, 1, 0, 0, 0, 1. Okay, so 241 as a binary number is the remainders read from or written from bottom to top. So 1, 1, 1, 1, 0, 0, 0, 1. Okay, so this here is the answer. Okay, questions on that one? Okay. The same thing works for any base. You just divide by whatever base you want to change to. Can I go up a little? Yeah, sure. Is that good? Okay. All right, so let's do another example of this where we go from base 10. Let's do it from base 10 to hexadecimal. Okay. Sure, no problem. Okay. So let's say I ask you to convert the decimal number 177,130 to hexadecimal. Okay, write its hexadecimal expansion. Okay, base 16. So we're going to do the same thing. Okay, we're going to divide, but this time we remember we always divide by the base we want to change to. So we want to change to base 16. We divide by 16. So right, divide by 16. Okay. How many times does 16 go into 177,130? Well, hopefully you have your calculator handy. You divide. You see it goes in 11,070 times. And then the remainder will be 10. Okay. We keep going. I take my quotient, 11,070. Again, divide by 16. 16 will go into that number 691 times. Plus a remainder of 14. 691 equals 2. If I divide 1691 by 16, I get 16 goes into that 43 times, plus a remainder of 3. Okay. Next, we take our quotient 43 again, divided by 16. 16 will go into 43 2 times, plus a remainder of 11. And 16 goes into 2 0 times, plus a remainder of 2. Okay, so here again, our quotient is 0. Stop. Okay. Our answer will be the remainders written in reverse order. However, this is hexadecimal. So anytime I've got anything bigger than 9, I have to write it as its letter form. Right, so 11 in letter form, in hexadecimal form, 11 is B. 14 we said is E, and 10 is A. Okay, so the answer is that 177130 in base 10 in hexadecimal is 2B3EA. Okay, so that here would be our answer. And it would be the same thing for base 8. You would just divide by 8. Okay. So far we know how to go from decimal to any other base and from any other base to decimal. Okay. We've discussed 3 bases: binary, octal, and hexadecimal. If we want to convert from binary to one of the other bases, meaning base 8 or base 16, we can also do that directly. Okay. All right, so let me show you how to do that by way of example. Let's say I ask you to find the octal and hexadecimal expansions of the binary number 111110, 1011, 1100. Okay. By the way, just as a side point, in general, when I write out a binary number, and your book does this, I write it out in blocks of 4 just to make it a little easier to read. Okay. You don't have to do that. Okay, so here's a binary number: 11, 1110, 1011, 1100. Okay. We want to find its binary expansion. Excuse me, it's a binary number. We're going to find its octal and hexadecimal expansion. Okay. So for octal, so go from binary to octal. What we're going to do is we're going to take this binary number, and starting from the right-hand side, I'm going to break it up into blocks of 3 digits. And then I'm going to convert those 3 blocks, okay, to octal numbers. All right. So let me rewrite this here: 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Okay, so I'm going to break this up into blocks of 3, starting from the right. Okay, and then I'm left with the 2 ones at the beginning. Okay. Okay. What I'm going to do now is convert each block to the digit that it represents in octal, which is really the same as its decimal number. Okay. So 100 is the number 8, right? Remember 100, that's 0, the first 0 is the ones place. The next is 2 to the 0. The 1 is 2 to the power of 2. Okay. So I said 8, I meant 4, excuse me. So that's a 4. Okay, this number here, 111, all right, that's 4 plus 2 plus 1, which is 7. Okay, this number here is 2. 111 again is 7, and 11 is 2 plus 1, which is 3. Okay. So you convert each of these blocks, you get 37274. That is its octal expansion. Okay. Why blocks of 3? Because this way, each block of 3, the largest it can be is 7. Okay, and 7 is the largest digit I'm allowed to use in base 8. Okay. Okay, so I look at each block of 3 as its own individual thing, and I convert it to whatever number that is. So 100, as I said, is 4 if you convert from binary. 111 is 7, and so on and so forth. Okay. For binary to hexadecimal, All right. You're going to break it up into blocks of 4 digits. Okay. So I have the number 1 1 1 1 1 0 1 0 1 1 1 1 0 0. Okay. So I break this up into blocks of 4 digits. Okay, and then I've got the 2 extra ones at the beginning. And then I'm going to convert each block into the number that it represents. Okay, and each block will be a number less than 16. Okay, so the first one here is going to be 8 plus 4, which is going to be 12. All right. The next one is going to be 8 plus 2 plus 1, which is 11. Right. The next will be 8 plus 4 plus 2, which is 14. And this last one here will be 2 plus 1, which is 3. Okay, so, and hexadecimal 3 is 3, 14 is E, 11 is B, 12 is C. So this is the number 3, E, B, C in hexadecimal. Okay. If you wanted to go from hexadecimal or octal directly to binary, you would just do the reverse of what we just did. Okay. So, for example, let's say I gave you 3EBC and I told you to convert that to binary. Okay. What you would do is you would take each digit here, right? I would write them out as their digits. So E would be, I would write as 14, B as 11, C as 12. I would convert each of these into a binary number so that it's a block of 4. Okay, so 12, I would write it out as a binary number, 11 as a binary, 14 as a binary, 3 as a binary, and I would write it out as blocks of 4 numbers, right? So 3 would be 1, 0, 0, 1, 1. 14 would be, what is it? 1, 1, 1, 0. 11, 1, 0, 1, 1. And then 12 would be 1, 1, 0, 0. Okay, and that would be it. That is a binary number. And if you wanted to go from octal to binary, you would write it out as blocks of 3 digits. Okay. Okay. So, for example, let's say I gave you the following example. Convert 765 from base 8 to binary. Okay. You're sort of going through decimal. Okay. Okay, so I'm going to write 765. I'm going to separate the digits here. I'm going to write each digit in its binary form. Okay, and I'm going to write it as a block of 3. Okay, write each digit in binary as a block of 3. Okay, and you would add leading zeros if you need to. All right. All right. So what would 5 be as a binary number? 5 would be 101 as a binary number. Okay, right. That's 1 plus 4, which gives me 5. 6 as a binary number is 110. That's 4 plus 2 without any ones. 7 as a binary number is 111. So the binary expansion of this thing is 111, 110, 101. Okay. That's 765 written as a binary number. Okay. All right, any questions on that? Okay. All right, so that is basically what we're going to do in section 4.2. We're done with that. In the time that remains, we got about 10 minutes left. Let's begin section 4.3. Okay. All right, any final questions on 4.2? Okay, so 4.3 deals with prime numbers or primes and greatest common divisors, and we'll also discuss least common multiple in this section. Okay, so let's start with the definition of prime numbers. Okay, have a good day. Take care. Somebody had to leave early. Okay, definition. An integer, p, greater than 1, is called prime if the only positive factors of p are 1 in p. Okay, so an integer p greater than 1 is called prime if its only positive factors are 1 and itself. Okay, a positive integer greater than 1 and a positive integer greater than 1 that is not prime is called, it's called what? Anyone remember what a number greater than 1 that's not prime, what it's called? It's called composite, okay? So every integer greater than 1 is either prime or composite, okay? So what are examples of prime numbers? What's the first prime number? What's the smallest prime number? Yep, 2. It's also the only even prime number, okay? The next would be 3, then 5, then 7, okay? Next is 11, then 13, then 17, then 19, then 23, then 29, and so on and so forth. Okay, so those are all prime numbers. Their only positive factors are 1 in themselves. They're only divisible by 1 in themselves. Okay, these are primes. What are composite numbers? Well, the first composite number, the smallest, is 4. The next is 6, then 8, then 9, then 10, 12, then 14, 15, and etc., etc. Okay. How many prime numbers are there? One is neither prime nor composite.
Hi.
Hello? Okay. So somebody said, I asked before how many prime numbers are there. Somebody said nobody knows. That's not exactly the correct answer I'm looking for. The answer I'm looking for is basically there are an infinite number of prime numbers. Okay. I'm not going to really prove that today, but let me just give you that theorem. And so there are infinitely many primes. Okay. All right. The next theorem that I want to discuss was there some debate on that? Not to my knowledge. There are actually several different proofs that there are an infinite number of prime numbers. Okay, so there. Okay. No problem. Okay. So the next theorem is called the fundamental theorem of arithmetic. Okay. It's as follows. Every integer greater than 1 can be written uniquely as a prime or as the product of two or more primes. Where the prime factors are written in order of non-decreasing size. Okay, right. And so in other words, the fundamental theorem of arithmetic tells us that every integer greater than 1 is either a prime number, or if it's not prime, meaning it's composite, then I can write it as a product of prime numbers. Right? So in other words, the primes are the building blocks of the integers. Okay, every number is either prime or a product of primes. Every integer. If it is a composite number, meaning it can be written as a product of prime numbers, then I can write that product in a unique way where I start with the smallest prime factor and then slowly increase until I get to the largest one. Okay. So for example, let's say we look at the number 100. Okay. 100 is composite, it's not prime. But I can find its prime factorization, meaning I can write it as a product of prime factors. Okay. So we can write 100 as a product of its prime factors, right? And that product is called its prime factorization. Okay. So if I want to write 100 as a product of its prime numbers, I have to figure out what its prime factors are. Okay. One way to do that would be to, so to speak, use a factor tree. I don't know if anyone remembers ever using a factor tree before. Right? So the way a factor tree works is I'm gonna think of two numbers that I can multiply to get 100. Okay. Give me two numbers that I can multiply to get 100. 2 and 50. Excellent. Okay. So 100 is 2 times 50. Okay. Now 2 is prime, so that's done. Anytime I get to a prime number, I stop. I go to the other branch. 50 is not prime, it's composite. I can write 50 as, I'm going to break that up into a product. So I'm going to write it as 2 times 25. 2 is prime, so I stop. 25 I can write as 5 times 5. Okay. So these prime numbers, 2, 2, 5, 5, those are all the prime factors of 100. So the prime factorization of 100 is, and I'm going to write them out in non-decreasing size, meaning starting with the smallest prime factors and going up in size. So I write 2 first. Okay, so 100 is equal to 2 times 2 times 5 times 5. And then what we usually do is, instead of writing it as 2 times 2 and 5 times 5, we use powers. So this is 100 equals 2 squared times 5 squared. Okay, so this here would be the prime factorization of 100. I can write 100 as a product of prime factors, of prime numbers, uniquely. It's 2 squared times 5 squared. Okay, so those are its only prime factors. It has no other prime factors. Okay, so this is the prime factorization of 100. Okay. Yes. You could have also done 5 times 10 or 20 times 5 times 4. That's fine. And you just got to keep breaking it up until you get to only prime numbers. And at the end, you will always end up with the same prime numbers. Okay, so it doesn't matter how you break it up as long as you keep going until you can't break it up anymore. Okay, so you could have done 2 times 25, 4 times 25, 5 times 10, whatever you want. Okay. Any questions on that? All right. All right, so I guess I'll end today just with a quick note that prime numbers and prime factorization, prime factors are used in public key encryption and RSA encryption. Right, they're an important part of that. Just without getting into it too much, basically, the idea is that it's very, very hard to find prime factors of very, very, very large numbers. Okay, unless you know what the prime factors are beforehand. Okay, that's sort of a basic idea of it. Yes, I'm aiming for this week. Okay, to get your grades back. All right. All right. Let's stop here for today. Let's do the attendance now, and I will see everybody on Wednesday. Right? We have class Wednesday, I believe, right? No class on Wednesday? Okay, so if there's no class on Wednesday, I'll see everybody next week. Okay.
Yeah, Wednesday is a Friday schedule.
Oh, okay, fine. So then everybody enjoy your Friday on Wednesday, and I will see everybody next week. Okay. Yes, I'm here if you want to discuss. Yes, yeah. Okay. All right. Once you've given the attendance, you can head out. And I'll see everybody. Okay, I'm going to stop recording here.
Professor, can you hear me?
Yes, just give me one moment.